So now comes our next topic of differentials. And so the idea behind these tangent line approximations is often formulated in the terminology or notation of differentials. So it's a similar process, just new notation now to build that. So if y equals f of x is a differentiable function, then this differential dx is considered an independent variable, and it's kind of representing the change in our x value. The differential dy, on the other hand, is defined in terms of dx, and it's given by the equation dy is the derivative times dx. So your differential dy is dependent. So what are these pieces actually representing? What do they mean in terms of our picture? So we're going to go ahead and we're going to go through this process pretty slowly. So we have some function, y equals f of x. And we now know how to find a tangent line at this point. So we're going to call this point P. And you can go ahead and get a rough sketch of the tangent line. Okay. What we're going to do is we're going to look at another point. We're going to go ahead and look at another point a little further away from x, which is basically we're starting at x and we're going to add this quantity delta x, so the change in x. The difference between these two, is delta x, so it's our change in x. That's really exactly what this differential dx is. It is the true change in your x value. Okay. Corresponding to this point that I've added, I have another point here that I'm going to call R on my tangent line. The point on my actual function, I'm going to call Q. Okay. And so here is what we get when we plug in x. Okay. Basically, this differential dy is going to represent the change in y on my tangent line. Delta y is representing a true change. So we're going to go ahead and draw in some lovely little triangles. Got a right triangle right here, and I'll call this point S. Okay. This is our dx, or delta x, representing the change in x. The change here is the true change in y values. So that's delta y. This differential dy is going to be the change in y values for the tangent line. So ultimately, the slope of this tangent line is the differential dy divided by dx. Okay. That is all that's representing. This dy is telling you what the change in the tangent line is for those particular points. Delta y is representing the true change in the function values. So to sum this all up nicely in words, the points P, which is x and its y value corresponding to it, and the point Q, which is going to be this value, x plus delta x, and the true y value corresponding to it. These are on the graph of our function. The change in x is delta x, and the corresponding change in y is going to be the difference in the y values here. So the y value at Q minus the y value at P. Okay. The slope of our tangent line is f prime of x. So our change in the tangent line is the change in y over the change in x, which is dy over dx. So just rearranging things, dy is f prime of x dx. So basically, this differential dy can be thought of as the directed distance from S to R. So what is that distance to that tangent line? Okay. And then in other words, dy is basically representing the amount the tangent line rises or falls, where delta y is representing the amount the function rises or falls. Okay. So we've used this notation dy over dx to mean these rate of change is that Leibniz notation, but it's also representing differentials. So it's giving us that slope of the tangent line. It is the change in my tangent line, y values, divided by the change in my x values. So we're going to try a few examples of this to kind of see that the true change in y is going to be close to our differential. So we're going to start by using the information to evaluate and compare the real changes in y's and this quantity dy. The function we're using is x to the fourth. We're looking at x equals 1. And the change in x we're going to consider is positive 0.1. Okay. So what I'm going to do first is draw a little bit of a picture, because we know what x to the fourth looks like. It goes through the point 1, 1. Okay. And so the graph of this function looks a lot like a parabola. Okay. And so this point here would be 1, 1. And then my change in x value is 1. My change in x is 0.1, so this would be 1.1 that I go over. So this is delta x, which is dx. It is 0.1, the distance between these x values. Okay. So we can figure out what the tangent line is at this particular point, but I'll go ahead and kind of go sketch it in. This is our tangent line, and that point goes through 1, 1. Okay. If I figure out what this y value is, it's 1.1 something. Don't know what that is. But drawing in a nice little triangle, this quantity here is going to be exactly dy, so my true change. So it is the change in y values on my tangent line. Where on the other hand, this quantity is going to be my delta y. And so I can figure out this point. It's 1.1, the y value. The y value corresponding to it is 1.1 to the fourth, and I can figure out the true change in y values. Okay. So delta y is going to be my function evaluated at my starting x value plus the change minus my original x value. So really, I'm going to see what is my function evaluated at 1.01 and subtract the original function value. So my true change in y values is 1.1 to the fourth minus 1 to the fourth. And if you plug this into your calculator, it is going to be about 0.464. So that's approximately my true change in y values. Now I want to see what is the change in the y values on my tangent line. And so our differential dy is the derivative times dx. So our function is x to the fourth. The derivative is going to be 4x cubed. Okay. So dy in our case is going to be 4x cubed times dx. So plugging in all the pieces, x is 1 and delta dx is delta x. It's 0.01. So plugging in the pieces, x is equal to 1, so it's going to be 4 times 1 cubed. Dx is 0.1. So going through and multiplying that, you get 0.4. So the true change in y value is about equal to the change in y of our tangent line. So delta y is about equal to this differential dy. Okay. So let's try a second example. Let's just find the differential of the function y, which is x divided by 1 plus 2x. So I'm going to label this as my function. Our differential dy is f prime of x dx. So I just need to find the derivative of this function. So we get the low function, d high, minus high, d low, all over low, low. Taking those derivatives, derivative of x is 1. Derivative of 1 plus 2x is 2. And then the denominator is 1 plus 2x squared. So simplifying this, that's 1 plus 2x minus 2x divided by 1 plus 2x squared. And then nice things happen, the 2x's disappear. Our derivative is 1 divided by 1 plus 2x squared. So ultimately, the differential is dy equals 1 over 1 plus 2x squared times dx. And so then I could go ahead and utilize this formula to find the differential at any specific x and any specific change in x value. Okay. So one last one, we're going to use differentials and the graph of f to approximate the following. So we've got this function, which we have no idea what that's going to be, but I do know what the tangent line looks like at the point 2, 1. And the first thing we want to do is approximate what is the function at 1.9, which is roughly around here, okay? So what I want to do is we want to use the tangent line which is f of x being approximately equal to this tangent line to help us figure out what this quantity is. So then this is when x is around equal to 2. Off. Lay down. No. Off. 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 Almost done. Stop it. So we're going to first approximate what the function evaluated at 1.9 is. And so the true value is close to this value of 2, but I have no idea what the equation of this function is. So I've got to utilize something else. Okay? And this is where that tangent line is going to come into play, because the tangent line is about equal to the function. So we're going to use the tangent line to approximate f of 1.9, since our function is about equal to the tangent line when x is near 2. So x is about 2. Okay? So I need to find the equation of the tangent line. And all I know is it passes through the point 2, 1. And then utilizing the graph, the slope is down 1 over 2. So its slope is negative 1/2. Okay. So plugging everything in, y minus the y coordinate is equal to the slope times x minus the x coordinate. So y minus 1 is negative 1/2 x plus 1. Adding 1 over, y is negative 1/2 x plus 2. So roughly, our function is about equal to negative 1/2 x plus 2. So we want to see what is our function evaluated at 1.9. So if we plug that in, this would be 1.9 divided by 2 is negative 0.95 plus 2. So this is around 1.05. So f of 1.9 is about 1.05, which makes sense. The y value is not going to be too far off from the 1. Second part wants us to find what the function evaluated at 2.02 is, roughly. And so we can go ahead and just use the tangent line again. So this is about equal to negative 1/2 times 2.02 plus 2. 2.02 divided by 2 is 1.01, and that's negative, plus 2. So that is 0.99. So f of 2.02 is about equal to 0.99. Okay. So these tangent lines and differentials are really useful. They're really just applications of the tangent line. So these tangent lines and differentials are really nice because then they can help us approximate the function values. They're much easier to work with because they're going to be linear, they're lines. And when you're dealing with complicated functions, a line works a lot better. If you have to go on to Calc 2, you're going to learn about something called Taylor polynomials and the Taylor series. And that's going to be how you can approximate functions with like a second degree polynomial, a third degree polynomial, a fourth degree. And so again, polynomials are really nice to work with, and they're easy for computers to work with as well. So you get a lot of nice simplification of processes by using these types of approximations.